Everybody, can you hear me?
Yes, we can hear you, Michele.
Okay. Okay, so we should start. Unfortunately, today the lecture is completely online because of the Zona Rossa situation. And we will continue from the point where we stopped last time. That was the topic on efficiency of electrical motor. Last lecture, we discussed about the different kind of electrical motors, especially the DC motors, which is the direct current motors that are mostly used in robotics. We analyzed some of their characteristic, steady state characteristics, finding out the relevant point like the null speed, the stall torque, etc. And we compute also the power, finding the parabola shape with a maximum almost at the middle of the stall torque. Now we will analyze the efficiency, finding that also the efficiency has a similar behavior, similar but not the same. We will see that is a shifted parabola with a different maximum. So the maximum efficiency point will be different from the maximum power operating point. Okay, let's go on. To find the expression of the efficiency, we need to consider also the Coulomb friction, tau C. And the efficiency is expressed as the ratio between the output power and the input power. And we see why we consider also the Coulomb friction, because the part of the torque that goes into Coulomb friction to counteract Coulomb friction doesn't generate any motion. So it doesn't generate any output power to the motor. So we have tau m, which is the motor torque, minus tau c, the Coulomb friction, times the omega, which is the velocity of the shaft, divided by the input power, that is the electrical power, voltage times current. And if to find efficiency maximum point, it's convenient to express the efficiency about the current. So we just replace the expression of the tau m here, and we express these ratios explicitly, and we replace the expression for the omega, voltage minus R times I divided by K, where K is the speed constant. And if we rearrange this expression, we find out that we still have a quadratic formula, quadratic expression that divided by a linear expression. And if we want to find the maximum of this, we see that is a parabola, but not quite a parabola, but a shifted parabola, a little deformed one. And if we want to find the maximum of this, we know that we need to do the derivative. The computation is a bit more involved. I let you do for exercise. And you can find the value of current that maximizes efficiency. That is Coulomb friction times voltage divided by Kr square root. And therefore, if you plot, we see this shifted parabola for efficiency. We see the maximum point is more close to the no load situation. So it's not for big load, but it's for small load. And we see here the two relevant points. So if we look qualitatively at the expression of stall situation where the velocity is zero and all the torque goes into a stall torque, we see that this term is way bigger than this one, and these two nullifies, and the efficiency increases with the velocity. But then after some point, for low torque, which is in this situation, the Coulomb torque starts to be important, or they start to be similar, these two terms. And so there is a situation in which these two terms becomes equal in this situation, and there is a decrease in efficiency according to the situation where we have close to the null load situation, and going to zero efficiency in the situation of null velocity. That is a situation where, in essence, the torque contract friction. And it is advantageous to have an efficiency curve that is flat, of course, because we want to be able to keep, if we want to control speed in a big range of values, we want to have efficiency as constant as possible. So due to the fact that DC motor efficiency has this shape, they are not the best candidate for variable speed application, unless we will use some more sophisticated control strategies. Any question about this? Everything is clear? So we can summarize what we saw till now. Yeah, on the x-axis, we have the torque that the motor can produce, or the load torque that can be delivered to the load, from 0 to the maximum value of the stall torque. And as a function of this torque, we have different curves. We have the current that increases with the torque, starting from the null load current, which is the Coulomb friction, going to the stall current, which is the maximum current. When we have the no load speed here, that is the velocity at which the motor spins at maximum speed. And as long as you start to attach a load, the operating point will move according to the low value to lower speed till the stall situation where the loads doesn't move anymore. The yellow line represents the power, is a quadratic function with some maximum, and goes from 0 to 0. If you have zero current, then you don't have power. If you have no motion, also you don't have zero power, because the power is product of velocity times torque. And the efficiency in general is around 85% at its maximum, or 90%. And you see that the peak is different from the power situation. And we have another point that is the rated operating point. Of course, when we talk on operating point, is a point corresponding to the torque velocity curve. So a tuple of composed by velocity and torque. And the rated operating point is kind of in the middle of the maximum efficiency point and the maximum power they will deliver to the load. And why the maximum power? But why we don't go to the maximum power, for example? Because in general, the maximum power point is a point where we have a lot of heating in the coil, and so we can have overheat. And the maximum efficiency in general is too low. It's not the maximum speed and torque we can get without overheating. So the rated operating point is the one is best for the motor, that is the maximum torque and the relative speed at which the motor can operate continuously, so steady state without overheating. And usually is related to the thermal characteristics of the motor. Here we see an example of a data sheet with the maximum operating point efficiency. And we see that the efficiency here is around 85%. We have power around under 60 watt maximum power. So this is a medium size electrical motor with a small size, I would say nowadays. So this is what you find in your data sheet whenever you want to buy the motor. And in general, we can choose the supply voltage we want to drive the motor, for example, 24 volts, 48 volts. And the choice of the supply voltage usually follows from consideration where you want to have the no load speed. So you divide the supply voltage by K and you get the no load speed, and according to the value of the no load speed that you want to have, that is close to the maximum efficient, to the rated point, that is the speed you want to drive your actuator most of time, then you can obtain the voltage. While the choice of the rated current depends on how much output torque we want to give to the load, again, on average. So here are some limits, performance and limits of DC motors. In general, the power can range very much from 10 to the -3, very small micro motors, to 10 to the 6 to the power 6 watts. In the case of the brushed motors, as you know, we have sparks, we have problem with commutation, so we have a limit on the angular velocity also due to that. In the coil, we can have overheat, and overheat creates a loss of insulation in the coatings that cover the coil, and this creates short circuit. So most of the times, the reason for which electrical motor damage is due to this loss of insulation and short circuit. And so we have a limit of the current due to this overheat. And also there is a limit on the current, on the torque, because there is a saturation in the magnetic circuit. If you increase the current after some point, you will see that the magnetic field increase and the torque increase, but after some point, there is a saturation. So there is no more increase in the magnetic field and the torque, while you can still increase the current, and this is a saturation point. And inside these limits, the DC motor can have a good efficiency of up to 80–90% of efficiency. So if we summarize all the relevant parameters, these parameters are usually stated in data sheets that are the documents that the manufacturers provide you, that it's your starting point to select the motor for your actuation system, to design your actuation system. They usually, we will use SI units, but be aware that most of the data sheet, they don't use SI units, they use run per minute. So we have what we call the supply voltage, that is usually called nominal voltage. And we say this chosen according to the no load speed or what is safe for the brushes. If you have a brushed DC motor, we have the rated power, which is the power related to the maximum continuous torque we can provide without overheating. The maximum power point, operating point, so the maximum power at that we can deliver. And we have a no load speed, no load current, maximum continuous current that can be rated current or IC as a symbol. You can find both of them. Starting current, which is also the stall current, rated torque, also called maximum continuous torque, or tau TC, again related to the maximum continuous current. Stall torque, same as starting torque. The terminal resistance, the resistance of the coil, measured in ohm, and you can measure it with a multimeter usually. The terminal inductance, measured in Henry, the inductance of the coil. You can have LCR, I think, multimeter to measure also capacitance, to measure that. And you have electrical time constant. We saw that tau L, that is the ratio between the inductance and the resistance, and is what it takes to reach 63% of the final value of the current, for example. And the mechanical constant, tau M, that is what is required to get the 66% of the final speed, of the steady speed, under a constant voltage input. And we have a maximum efficiency, and finally the torque and the speed constant, that in SI units, they should have the same value. And here you have two examples of data sheet. We have a 25-watt motor that you can drive different voltages. So in general, you have different designs for different voltages, maximum voltages, because you need different insulation capabilities. And then you have the relevant point that we discussed, the no load ones and the rated load speed and current and torque. And finally, you have the stall current, the starting current. And here we have another data sheet with a bigger motor like 40 watt. And we will see that we can see that the rated torque it's higher for a bigger size motor. Everything's clear? An important remark is that some manufacturers can give you the torque output already with the reduction transmission incorporated. So you need to be careful to read if the gearbox is included, because you might get a high torque here of what is actually the motor delivering. So now we saw the characteristics. We said that the no load speed, or the speed, it's related to the voltage. You remember the curve can shift with the voltage. So if you want to change the speed, we might want to control the voltage. And the purpose of a motor driver, because you remember our signal controller as a signal in a low power domain, and we want to drive the driver. It's able to adapt this signal, low power signal, to a desired high power signal. And so we said that to keep, if we keep the voltage constant, the steady state speed is dictated by the load torque according to the torque speed characteristic. But if you want to change the speed, we can change also the supply voltage. And to control the voltage, we will see that we use a motor driver, and we can say that if we change the voltage very quickly, the controller, the motor reacts to the average voltage sent by the driver and by the controller. And so we have two strategies to adjust the voltage. We saw that we can use a voltage divider, and this is quite inefficient because we lose a lot of power for heat because we need to do a voltage divider, and the voltage on one of the two resistors is just it's burned in Joule losses. Or we can use a H-bridge circuit. And an H-bridge circuit is the most efficient way nowadays used to control the voltage for driving an electric motor in a motor driver. And let's consider, for example, a case of one-phase motor, not a three-phase motor. We see the extension afterwards. And in the case of one-phase motor, the driver is composed by 4 switches. And these switches are called MOSFETs that are power transistors. They have small dimensions, small resistance, and small power loss in the on-off states. You can still have some power loss during transient between on and off, but these transient typically are very short. And this is the schematic of H-bridge circuit. And we see here that we have no current through the motor, but if we close these two, for example, switches, MOSFETs, or these other two, we have a current flow going in one direction or in the other direction through the motor. And we see that each side of the motor can be either connected to the positive voltage, or as this case, to the negative voltage. And only one in each side of the H-bridge, of the MOSFET of each side of the H-bridge should be turned on, because otherwise you will have a short circuit between positive and negative of your battery, and you don't want that because you can have melting of cables, and it's very bad. And the advantage of a H-bridge circuit that tells us that is the reason for which it's so efficient is that we always apply the maximum voltage all the time, and we work on the duty cycle to apply this voltage not all the time. I mean, what do we apply? We apply the maximum voltage, but we don't apply the maximum voltage all the time, just a fraction of a period, where a period is a very high frequency square wave. So this is the period of the square wave, let's say is around 10 kilohertz usually. And adjusting the time where we apply the maximum voltage, that is the called the on time, while the duty cycle is the ratio between the on time and the period. We achieve what is called a pulse width modulation, PWM. And as I said, the PWM frequency is way higher, several orders of magnitude higher than the highest frequency we want to drive the motor. And as I said, the range is from 2 kilohertz to 10 kilohertz. And because of this high frequency, and because of the coil inductance that you remember, inductance is a component that opposes to abrupt current variation, the motor responds to the average voltage of this square wave curve. So if we have a very short duty cycle, the on time will be very short and the average will be a very low voltage. If we increase the duty cycle, that, for example, with a microcontroller, we can increase the average voltage, and still, if we almost have here the example of the 90% duty cycle, we always have that the average voltage is equal to the maximum voltage. In case of a three-phase motor, a BLDC motor that we saw previously, instead of 4 switches, you have 6 switches. You connect the 3 phases of the 3-phase motor that is here, you see is connected in a star connection. I won't go into the details of differences between the star connection and triangle connection, just know that exist. And these switches are are open or closed in a way such that we have trapezoidal waveforms for the magnetic field at each phase. And to do the switching, we need to know the position of the rotor of the motor. So again, remember the Hall sensors, we achieve the position feedback of the rotor. And a microcontroller implements the PWM modulation to determine the triggering instance of all the switches in order to achieve the rotating field. So it's called a DC motor, BLDC motor, because here we have a DC current, a DC voltage. So the voltage here, if you have a 380 AC supply, we need to put through a rectifier bridge that from the AC will produce the DC voltage. Finally, there is an improvement of this switching that is usually creating only this waveform. But we know that from the DC motor, when you explain the working principle, that we have a force that we call quadrature force, that are these two forces that create a torque, while the other two nullifies, and they are called D force. And the D force, the field around the control is a trick to control the current flowing through the statoric coils in a way that we minimize the force or the torque, the forces that are not on the coils that are not producing motion. We maximize the quadrature force. And this allows us to shape and improve the torque speed characteristic of our DC motor, increasing the operating area. This is very nice because it allows us to achieve higher speed with higher torque and also have higher motor drive efficiency up to the 97% in certain applications. And with this trick, our DC motor or BLDC motor becomes much better for variable speed application, which are the ones we use in robotics. So be aware that inside your robot, mostly or likely, you have a field-oriented control strategy implemented inside the motor board. Everything is clear? If you have any questions, just unmute your microphone and stop me. We said that it's possible to control the voltage, to control the speed, but in robotics, we sometimes want to control the current that is we saw directly related to the torque we apply to our actuator. And in this case, if we want to control the current, we need a current feedback loop. So we need to measure the current through a sensor. And usually this sensor is called shunt. It's a shunt resistor. So very low, simply very low resistance resistor, and where across which we detect the voltage drop. And because of the Ohm law, we can get the current dividing the acquired voltage drop divided by the value of the resistor. And this is a very common and highly reliable choice to measure the current and commonly adopt in many applications. So our controller takes feedback from the current through the motor and drives the voltage in a certain way, trying to achieve a desired current. We need to be aware that this current controller, this current loop should be much faster of the mechanical dynamics in order to achieve a certain decoupling. We see that separation principle in dynamic control system tells us that if we have an inner loop with very high frequency and an outer loop, for the outer loop, the inner loop be an ideal tracking. For example, you can consider the current is tracking perfectly the desired one for the outer loop. And this is usually the case because this current loop, they go usually from 5 kilohertz to 20 kilohertz, while our mechanical constant are much lower. How do we choose the voltage to achieve this tracking of desired current? Let's apply a voltage that has this shape, this formula, and if we try to replace in the electrical dynamics, we see that we have here the electrical dynamics. We see that these terms that is related to the back MF will cancel out. So we need to be aware that a proper cancellation will not occur really because our estimated value of the back MF constant might be slightly different from the real one. So we will have a remaining disturbance due to this model inaccuracy. And if we define the current tracking error as I minus desired current, we can see that we have the derivative of the current on one side equal to this R plus Ki, where Ki is the proportional gain. We will see what the proportional gain is over controller divided by L. And this means that if you replace the derivative of the tracking error, you get, if we consider, for example, di over dt minus did over dt. So this is what we get. If we replace and we get the derivative of the tracking error is equal to AI divided tau L, where tau L is not really what we used to have in the open loop situation, but it's slightly different. So the proportional gain of our controller, Ki, so this is it's reducing our electrical time constant. So it's kind of speeding up the electrical dynamics. And for a constant input, we have this equal to 0, and we have a first order differential equation that you know how to solve in closed form, and the solution is the evolution of the tracking error is exponential, negative exponential of t over this tau L times the initial value of the tracking error. And forcing an initial condition to solve the differential equation, we know that if at the beginning the current is 0, the tracking error will be minus ID. And if we replace this minus ID in of 0, we get the expression of the current, the time evolution of the current, which is a first order response, where we know we have here a negative exponential that decays, because it's a negative exponential, this term will decay to 0 and for infinite time. So the current will go from 0 to ID, because 1 minus 0 is ID. And the way it converges to the steady state reference, that is the desired current, it's dictated by the electrical constant that we saw. It's very fast by itself. In general, we can make it even faster because we can increase this gain a lot, and we can reduce the electrical dynamics, increase the convergence of the electrical dynamics. And because of this difference in the time constant between the electrical and the mechanical one, we can consider that this inner loop make our current control infinitely fast, and we can consider that we are able to apply the desired current all the time for the implementation of, for example, a position or a speed controller. Everything is clear? Okay, let's move to the next.
Excuse me.
Yes.
Can you repeat how we choose the voltage command?
So
at
the
the beginning.
The voltage command we choose with a certain formula that I showed you before. So the voltage command depends on the kind of controller we want to implement. And this is the very specific case. Can you see the screen?
No.
Okay. Because I need to share other stuff. Okay. Okay, you should see now. You see?
Yes, yes.
Okay, so the voltage command in our case, let's say we want to control the current, the desired current at 5 Newton meter. And let's say this desired current comes from an outer loop. So we have, let's say, a controller that tries to control the position of the motor. And to drive the position, we saw that we were applying a certain voltage. But now we do something else. To drive the position, to control the position, we need to provide a desired current. So the controller output from the outer level for the position level will provide, will ask for a desired current. And the inner loop controller, that is a current controller, will have to track this desired current. And to do so, we'll apply a voltage. So now the voltage is not directly our control. So is not a output of the position controller, but is the output of the current controller.
Michele, maybe
Output position controller spits out a desired current to be tracked, and an inner loop, like you think about a smaller, faster controller inside, that is the current controller, will try to track this desired current applying a voltage. So the voltage is the output of the second controller, the inner loop current controller.
Nikki.
The voltage has this shape, so as we have some term dependent on velocity and on the tracking error of the current. So Ki here is, don't confuse with with what we see now with the proportion integral gain, because this is just a current proportional gain. Because in the next lecture we'll define differently this Ki. Okay.
Okay, thank you.
And if you replace this voltage in the dynamics, you see that the tracking error in essence goes to 0, because if you don't have any input, this differential equation goes to 0, and having the tracking error that goes to 0 means that the current goes to the desired value. So this is the equation that represents this time evolution of an exponential.
Michele, can you hear me?
Yes.
Maybe if you have access to the surface, you can draw the control loops so it is clearer where the signal comes from. Otherwise,
yeah. The problem is that I tried. I cannot share. I should share a screen from the surface, but I don't know how to check things.
Well, maybe
participants.
Maybe you can add an extra slide in this set for by the time that when they download, they can see where the control signal comes from.
Yeah. Sure. I will add that. Yeah. Good point. Yeah. I just noticed now that it's not so intuitive. This if you don't show the cascade loops arrangement. So let's go to the next one. That is a chapter related to transmissions. Can you see the screen? No. For some reason,
Not yet.
okay.
Now we can see.
Okay. Okay. So first, why we want to have transmission? Because we want to, as I said, sometimes we have a very big link to move, a very big load, and we have a small motor. And we still can do something with this small motor. We need a transmission in the middle. And transmission is to optimize the transfer of mechanical torque from the actuating motors to the loads. And this transformation is quantitative. For example, I can go from a low torque, high velocity motor to achieve a high torque, low velocity motion at the actuator, at the link, sorry. And therefore, we can see transmission as torque amplifiers. And the advantage of doing so, why we want to use more motors, is that they are lighter. So if we use more motors, we reduce the weight of the robot. We have a lighter robot, and we have less torque to require to move. But the price to pay is that we have a reduction also in speed. So the power is the same, but if we have low torque, high power, low torque, high speed, we have high torque, low speed. And the other transformation, the transmission allow is a qualitative transformation. So from a rotational motion, for example, you can transform to a linear motion, like the one you might need, for example, from the case of a prismatic joint. And or simply you want to locate the motors closer to the robot base. So you want to shift the axis of rotation with respect, for example, to the knee angle. You want to, instead of putting the motor here, you want to put it here. Why? Because you have less inertia to move, okay, in the structure. And we see that there are different arrangements and transmissions that allow this shift, like with the belts or chains. The quantitative transformation allows us to, as I said, to match the requirement of our robots that might require large torque and not so high speed, while usually we have in DC motor, we usually have low torque and high speed. We saw that the maximum efficiency point is the one, or even the rated operating point is the one that is closer to the higher speed area of the characteristic curve. So usually we prefer with the electrical motor to work at higher speed. And the transmission trades off speed for torque. We have some efficiency involved due to mainly friction. And as I said, the transmission acts as a speed reducer, torque amplifier. And usually the transmission is located after the motor, between the motor and the load. And here you can see a single stage reduction gearbox. Multiple stage means that you might have an arrangement of different wheels, teeth wheels, or gears, they're called gears. And in this stage, we call it a reduction gearbox because for every rotation of the motor, the output shaft rotates less, slower. And in general, transmission are defined with the gear ratio, which is the number of teeth of the load side wheel divided by the number of teeth of the motor side wheel, or the difference in rotations of the load side wheel with respect to the motor side wheel. And if this is bigger than 1, we call it reduction ratio. The output speed, do you have an idea of how the output speed will be related? The load speed will be related to the motor speed whenever you use a transmission. We said that the transmission works as a speed reducer. So in general, the load speed, it's equal to the motor speed divided by the gear reduction ratio N. So here you see the motor speed, the motor load, the motor inertia, sorry, this is represented by the gearbox, and you have the load speed. While due to the power equivalence, we said that power in is equal to power out, and we have the product of torque of motor times velocity of the motor is equal to torque of the load times velocity of the load. And because of that, and because of the previous relation, we get the reciprocal relation that tells us that the load torque is N times the motor torque. So the gearbox works also as a torque amplifier. It amplifies the motor torque, achieving a higher load torque at the load. Everything is clear? And one side effect of introducing a gearbox is not only the friction losses, but also the fact that it amplifies the inertia of the rotor of the electrical motor. The effect of the rotor of the electrical motor on the dynamic load. So since velocity are related to that, and acceleration is the first derivative of velocity, we have the same relation for the acceleration level. And if we want to accelerate the shaft, we need to provide a motor torque that has this shape. So we need to accelerate the motor, rotor of the motor. So we need to consider inertia forces to accelerate that. You have the friction, the motor's side, and we have the acceleration of the, sorry, this is load, Q double dot L times the inertia of the load plus the friction of the forces to move the load that are at the load side. And since this is a torque, is mapped into a load torque is mapped into a motor torque divided by M. And if we replace the motor acceleration with the load acceleration, we have n q dot L, and the velocity, we have n q dot L. And if we collect everything together, and we express we multiply by n to get the load side torque, we see this expression. So we collect everything and we see that the rotor inertia, it's multiplied by the squared of the gear ratio, and is increasing the load inertia. And if we have a big gear ratio, like 100, for example, in the case of an harmonic drive transmission, we can have a very high amplification. And even if the rotor inertia is small, if multiplied by this big number, this is 10,000, for example, it can become comparable and not neglectable in the load dynamics. And the same happens for the friction. So to accelerate the load, we need to waste energy also to accelerate the motor inertia, the rotor inertia, and this is becoming even more important if you have a big transmission ratio. So in general, we want to have a transmission ratio that is very large, because you can have very high torque, but the load. But we need to be aware that there are some technological construction problems. The gearbox, if you have a big N, becomes very big and cumbersome, big volume, and you certainly have higher friction, and also high amplification of the rotor inertia. So if possible, nowadays the trend is to use low ratio gearbox and try to use high density direct drive motor. So higher torque density direct drive motors that are able to, by themselves, apply a very high torque with a high number of poles. And we can compute the optimal reduction ratio. Now let's consider only inertial forces, neglecting friction, and we can express the torque at the motor this way, from the acceleration of the load. And if we want to find the optimal of this of this of the optimal point, we need to the optimal gear ratio. We need to minimize minimize the motor torque. We need to compute the derivative, this expression with respect to n, and set it to 0. And this is the derivative. And we see again it's a parabola with the second derivative positive. So it's a concave parabola, and it will have a maximum, and the value of the maximum is the one that nullifies this expression, and is the ratio between the load inertia and the motor inertia. And this is very similar to for the one that studied electrical circuit to the concept of impedance matching condition for circuits, for electrical circuits. It's just a mechanical expression. And so for the same acceleration of the load, we provide, this is the inertia reduction ratio that provides the minimum motor torque. And if we look at the different kind of transmission in robotics, we have the gears. We said that can have different arrangement. There are spur gears. In this case, they try to shift the axis of rotation. Or bevel gears, they allows, for example, rotation of the axis from vertical to horizontal. The problem of these are deformation and backlash, because the teeth may not engage perfectly. We saw this. With helicoidal teeth, you can reduce the backlash problem. We have the worm gears that convert rotational motion into translational motion, like the one we use for prismatic joint. And they are composed by a gear and a lead screw. This is called a lead screw. And usually have a very high reduction ratio, up to 1,000. And because of this big reduction ratio, we have problem of friction, backlash, and also elasticity. Then we have also belts, toothed belts and chains. And they, as I said, are used to dislocate the motor axis. Like we have in our quadruped robot called Solo, we have these belt transmissions that allows us to put the motor of the knee far away from the knee axis, very close to the shoulder. And the problem are compliance, because the belt can deform, or vibration induced by the larger mass and the chains, for example. The most famous transmission that is used in robotics is the harmonic drive. It's been widely used in the past. It has a very high gear ratio, up to 200, from 100 to 200. The main problem is related to elasticity, because there is a flexible element. We will see here the principle of operation of an harmonic drive. An harmonic drive is composed by three elements: a wave generator, that is an elliptical, slightly elliptical part that is coupled to the motor. And the wave generator is placed inside another element that is called the flexible spline, which is a flexible element with some teeth on the periphery, on the around. And this flexible spline is placed in another part that is called circular spline, which is a rigid element with another set of teeth. And the circular spline is connected to the load. So the circular spline has the teeth inside, while the flexible spline has the teeth outside. And in general, the number of teeth of the circular spline, it's slightly bigger than the number of teeth of the flexible spline. For example, 2 teeth has 2 more teeth than the flexible spline. And the reduction ratio is the number of teeth of the flexible spline divided by this teeth difference. So if you have 100 teeth on the flexible spline and you have 2 teeth difference, we will have here reduction ratio of 50. And if we look at this animation, this is the marker. The tag will move, it started there. This is the wave generator that is slightly elliptic, that rotates and puts in rotation a flexible spline that engages on the circular spline. And when it goes back, does half rotation, we see that the marker that used to start here is the tag is slightly behind. So it's 1 teeth behind. So after 1 full rotation, we will see that the difference of the marker in the flexible spline is move of 2 teeth. This means that to make a full rotation of inside the circular spline, we need to rotate many times the internal shaft. And this is the way we achieve the reduction. This guy is not working, this animation, I'm sorry. I didn't put embedded this video. But I think I explained clearly enough the principle of operation of an harmonic drive. And the good thing of an harmonic drive is that they have inline construction, so they don't occupy space. They are very compact and slim, and the fact that they have a very high reduction ratio. And also that the backlash that they have, it's very small. Of course, you have a cons, and the disadvantage of this drive is that because of the flexible spline, we have a elasticity, so we have some stiffness in the transmission of the motion between motor and load. We see here that we have an electrical motor, we have the harmonic drive, and here we have the load connected to the circular spline. And these transmissions should be taken into account and modeled appropriately if we want to achieve high performance controller. And the way you model the transmission, the elasticity in the transmission, it's that is affecting the dynamics of the load, is by means of a spring damper model. So you have the spring representing the transmission elasticity and the damper representing the friction in losses in the transmission. And this is the inertia of the motor and this is the inertia of the load. And the equation of motion in case of doing this modeling increase the number of states, because we no longer have only, as you remember, sorry, no, we didn't see that yet. We don't have only the motor position and velocity states that reflects into load through simple multiplication by the gear ratio. But we both have states also for the load position velocity. And the two equations are linked by the transmission forces that are the elasticity and the damping of the transmission. Sorry, this is KT. I will correct this. Everything is clear about transmission? We could do a short break at this point. Or let's continue with the next topic. It's quite short, and we do a longer break. Maybe it's better. Octavio, can you see the slides?
Yes. Yes.
So in this part, we will discuss about some important points that are useful to make your simulation realistic, because as we saw, there are many issues in the sensors that are not, can be modeled or need to be considered to do a realistic simulation. And also in the actuators, we have non-idealities. And the non-idealities in actuators are mainly related to friction, backlash, and deadband. And in terms regarding friction, all mechanical system that have some moving parts, moving one with respect to the others, like for example, a joint, they have some sort of friction, and friction force has the peculiarity of being always opposing motion. This friction force, for example, in a joint is mainly related to the sliding parts, like the bolt, the bearings, that are the element that allows the rotation of the two parts of the joint, and they have balls inside, very strong ones, very, very hard ones, but due to the rolling contact and to the fact that the contact, even the small ball, the point, the contact is a point, but there is always a certain kind of deformation. There is some rolling friction, and so some friction in the bearing. So in the most famous model, it's the Coulomb model, and in friction, it considers that there are three components. One is the Coulomb friction, the other one is the viscous friction, and the stiction. And the stiction is called also static friction, and the viscous friction is always related to the motion. While these two components are happening when this is when there is no motion, and this is when there is motion, but is a constant value. So the viscous friction is also called damping. It's proportional to the velocities through the damping coefficient. Is normally called B. Sorry, it's lowercase b. And has this shape. So if we have the speed, now it's called, consider like a mass sliding on a plane, so a linear speed, positive linear speed, the force is always opposing the speed motion. While the Coulomb friction, it's coming from the Coulomb law, that is the most common model, mostly used model available. It's very old, was derived with many experiments back in the 18th century, and it says, the Coulomb law, that the tangential force during a sliding motion is bounded in magnitude by the normal force at the contact, and is bounded by a fixed ratio that is the friction coefficient mu. So if you have a normal at the contact, so the force applied, for example, by a weight of the mass on the surface, we multiply this by a friction coefficient that depends on the kind of surfaces that are facing each other, so on the natural surfaces. So you cannot say, if you have steel on a steel ball sliding on an ice, you cannot say that the friction coefficient of the steel ball is 0.3. You need to say that the friction coefficient of a couple surface, steel and ice, is 0.3. Then if you have the steel ball sliding on wood, you will have a different number. So it depends on the two surfaces. And the geometric interpretation that we often use in robotics, it's the fact that the friction force, saying that the friction force is limited in its tangential component with respect to the normal one, is the same as saying that the friction force itself stays inside a friction cone, where the size and the opening of the friction cone is related to the friction coefficient. So the bigger the friction coefficient, the bigger the cone. The smaller the friction coefficient, like if you are on ice, the smaller the cone. The vertex of the cone is at the contact point, and the size of the cone is the arc tangent of the friction coefficient. Everything is clear? So, if the contact, as the contact is sliding, then the magnitude of the friction cone force is exactly mu times the normal, and the contact force lies on the cone, on the boundary of the cone, in a direction that is opposite to the velocity vector. So it's minus fc. We will see fc depends on mu pen, sine of the velocity. Well, if the contact is not sliding, we have stiction force, and this stiction force, it's slightly bigger than the Coulomb force. It's the same thing. It's an additive force opposing the motion. Of course, the motion is a micro motion. And this stiction force is called static friction, and is the force that needs to be overcome to enable to start the relative motion of the objects in contact. And it's the same, as I said, of Coulomb friction force, but for zero velocity. You see here for zero velocity, we have the two values, and these values are slightly bigger than the Coulomb force. Putting everything together, we have the total friction force composed by the Coulomb part, the viscous part, and the stiction part. And we should underline that because of this different value of Fs and Coulomb force, we have a phenomenon called like Strybeck effect. That, I mean, this is a model, of course, that researchers in the 18th century found, but in the reality, what happens is that at the beginning, when the motion starts, it's a slightly decrease in Coulomb, in the friction force, and then an increase with the viscous part, as long as the viscous part starts to dominate. And the initial decrease is called Strybeck effect, and it's very dangerous. Because it has a destabilizing effect, because it's like having a negative damping. So while usually friction is good for the control, because we will see adds damping to the system and damping improves the stability of the system, the negative damping due to the Streibeck effect is bad because it removes damping from the system. And identifying friction, it's quite hard, and it can be dangerous also if you try to compensate, because of if you don't identify properly and you try to compensate directly, adding the friction forces to the control action, because of this not perfect cancellation, you can end up with this negative damping, destabilizing effect. So in general, it's better to add, for example, a sensor in a location where you have very low friction. In the case, for example, of IQ, of our hydraulic robot, we have the actuator, and the friction in this robot is mainly located in the seal, which is the between the sliding part inside the piston, of the piston inside the cylinder. And rather than measuring for example, the load torque by measuring the difference in pressure of the chambers, that it tells you the hydraulic force, you can measure the force that you apply, the piston applied by using the pressure difference of the chamber multiplied by the difference of area. And in this case, you will have to, this force will not the force that is applied to the load, but will consider also the friction. So it's better to apply a force sensor or a load cell after the friction part, the relevant part, and very close to the load. And in here, the only friction will be in the friction in the ball bearing, which is usually very low. Everything's clear about friction. Then we have also another aspect that I slightly introduced before, that is backlash. And backlash is related to situations when you have some clearance in a mechanism due to the gaps between parts, for example, the teeth of a gear wheel. And because of these gaps, the system might move in one direction, for example, like this direction, and without applying any force or on the next part, the mechanical sequence. And because of this lack of driving, we can have many problems, like limit cycles when we have oscillations and due to instabilities, vibrations, and it's very bad for control. Actually, if you have backlash in your system, you should try to remove it, because there is no control strategy that can help in whenever you have backlash, because you have under actuation, you lose actuation in some moment, and whenever you have a feedback control, the lack of actuation is very detrimental. And the only solution is to improve the mechanical design. Try to use conic feet, try to improve the geometric tolerances in your gears, machining of your gears, in order to remove the backlash. Finally, the last non-ideality we will present is the deadband. And the deadband is similar to backlash, but not the same. It's whenever you have a range of input values for which the system output is 0. So let's say you have your input, and in this window you have 0 output. Then you start to have a linear behavior, for example, between the output. This is, for example, present whenever you have hydraulic valves, when you have overlap hydraulic valves, where the spool, that is the shift the part that opens and closes the channels to the valve is having some overlap and is closing. It's closing completely the channel. So to open on the other direction, you need to do kind of motion where there is no flow. And this is appearing as a dead band. The other situation is whenever you have the MOSFETs in your drivers, and this MOSFET usually have some voltage drop due to the internal diode that is in the MOSFET. And in that case, when you reverse the voltage, you need to provide this voltage across the diode that will provide no current. And a backlash can be thought as an example of deadband for gears. And I said that it's not possible to compensate, but in case of valves, you can do that. You can do that by inverting the deadband. So you give a command that takes into account already this loss of input with respect to output and provides the opposite behavior. Okay, we can do a break now of 15 minutes, and we continue with the next slide. If you have any question, you can tell me now.
I've got a question about the stride back effect. Could you please repeat it very quickly?
Can you increase the volume of your mic? Because this.
Do you hear me?
Yeah.
I was asking about the stride back effect.
Yeah.
If you could repeat it very quickly. Thank you.
Yeah, the stride back effect is due to the fact that when you are the object in contacts are still, they are not moving, you have a stiction and you need to overcome, let's say Coulomb friction is 10 Newton and stiction is 12 Newton. So to start a motion, you need to apply a force of 12 Newton. After that, since there is no velocity, the viscous friction is 0, and the required torque to move the load is, the required force is no longer 12, but is 10. So, and this is according to the Coulomb model. But in reality, nothing is abrupt, is not dropping from 12 to 10, but is continuously reducing in essence at the beginning. Then whenever the speed increases, because viscous friction increases with speed, then the friction force starts to increase. Remember, the friction force is a sum of these two whenever is in motion, and is this whenever is still. So whenever going from this that is still, that is slightly higher, to something that is the sum of these two, you have these discontinuities. Nothing in nature is discontinuous, and what happens in reality is dieback effect, that is an initial decrease in friction force. So you start to accelerate more, and then a decrease, an increase of friction force. So, and this has the destabilizing effect that I was telling you about.
Okay, thank you.
Yeah. Okay. No other question. I put mute for a while. I'll see you there in 15 minutes. Okay, are you ready? Let's start after the break. Octavio, can you hear me?
Yes, I can hear you.
So here we just review a very common way of writing the dynamic equation for simulation. The dynamic equation of, in our case, our actuator, our DC motor, that is called the state space form. We want really implement this in our lab because MATLAB Simulink, it's doing the integration for you. But if you need to use another tool or implement by code your own simulator, you know that you need to perform the integration of the dynamics. You need to put the dynamics in state space form and call your integration function to obtain the evolution of your states. So it's important to know what a state space form is. We will also use that more forward in the course. We want to do the discretization of the state space form just because it's not useful for your lab, and it's additional information that we won't use right now. So if you look at the remember the Kirchhoff equation on the circuit of the coil, armature is also a synonymous of coil. We see the voltage equal to the drop in across the resistor, the voltage due to the change in current, which is the inductance, and the back EMF. Then if we look at the mechanical equation, we have the inertia of the motor, rotor, times the acceleration, plus the friction torque, and any possible external load torque. And to connect these two equations, we have the length law that connects the back EMF to the velocity of the shaft times the back EMF constant K, and the Lorentz law that connects the current, the motor torque via the torque constant. That happens to be the same as the back EMF constant. Now, to have a state space differential equation, we need to express our differential equations into this form, which means defining a vector of the states x, and we associated the first derivative of this state vector to a function that is a function of the state itself and of the vector of inputs. And in our case, in the case of our system, what are the inputs, in your opinion? Any idea?
Can you repeat the question?
What are the inputs in our DC motor actuator control? So our DC motor and load system that is described by these equations. What are the inputs of this system? External inputs.
The current.
No. No, because the current has an evolution, there is a derivative here that tells you how the current evolves. So the current, I would say, is more a state. What else?
The voltage.
The voltage, yes, is an external input. Do you see another external input here?
Maybe the load torque.
Yes, very good. We have two inputs here. One is the voltage, supply voltage, and one is load torque. So our vector of inputs is two-dimensional. And, sorry, in the states, what about the states? So the states are the ones that have variable that appear with some derivatives. And these derivatives are allowed to compute the evolution of the state. What are the states here in your opinion?
Current and angular velocity.
Angular velocity. Okay, yes. There is something else. So we see here there is a derivative of angular velocity. Yes. So angular velocity is a state. There is another state missing.
The current.
It's not the current is a state. Yes. It's not really. You will see in the state space equation is clear. Here is not so visible, but is the position. Okay, the position is also a state. Because we can rewrite this equation in a way that you will see that the position will appear with this first derivative that is the velocity. So the order of the system in this case is third order because we have three states. Usually we will see in detail in how many ways you can define the order of a system. There is not only one way, it depends on what you look at, but the system here is third order. We have velocity, position, angular velocity, and current. These are related to the mechanical dynamics, that is second order, and this one is related to the electrical dynamics, that is first order. Together, they make a third order system. And if you work out the acceleration from the mechanical balance in the current, I don't like to put I dot, so I explicitly say di over dt. From the electrical equation, I get these two expressions. And sorry, this I should have pointed at the beginning is the model of the system we are describing. So the pictorial representation of the system we are describing, where we have the supply voltage that drives a current into the motor through a resistor and a coil, and the motor drives the load. This is the back EMF that is transformed into it creates a voltage drop, and here you have a motor torque that is becoming load torque because we have no gearbox in it. And if we since these equations are linear, we can express them in matrix form as a linear dynamical system. Linear dynamical system is something that can be written in this form, and that is a state space form. And if we write the previous equation, we see that we can write, we have the state in this position, so I, theta, and theta dot, and we saw that the derivative of the I is I minus L over R, this term plus a term from velocity plus the voltage. So if we write this, we have the velocity terms here. Sorry, there is an error here. This should be here. I will correct this in the slides. And the second equation is what I told you. It's just saying theta dot equal to theta dot. So there is a 1 here. And the third equation is the one coming from the mechanical equation that tells you that the acceleration, you need to divide by you have a term due to the torque, motor torque, which is Ki divided by Jm. You have a term due to the friction, also this one is wrong, it should be here, multiplied by velocity, divided by Jm, and you have the term due to the load torque. And you see that whatever depends on the input, we put in an equation called B, is in a matrix called B that we call input matrix. And what depends on the states, we put in a matrix A, which we call state matrix. So here, what was missing in our electrical equation was V over L, and we see that this entry multiplies by V, and this one is multiplied by tau L, and will affect only the torque, the mechanical dynamics. So this is a test space form. The peculiarity is that it has first derivative of the state and a state matrix. This is a state space form for a linear system. You can have a state space form for a nonlinear system. In this case, you will have a function of x and u. In this case, since it's a linear system, you can separate the effect. Okay, it works the superposition of effect, saying that each input can affect separately the evolution from the state, with respect to state. And why a linear system? Why we like to have a linear system? Because an analytical solution exists for a linear differential equation. And so we can directly integrate this system in a closed form way. Or we can do it numerically, doesn't matter. Here you can see some results of the simulations with this motor that I'm not sure will be the one we use for the labs, but I think so. And during the labs, whatever you will have to obtain are these kind of graphs. Let's say this is what we saw are the simulations with a constant input voltage. We have, for example, 10 voltage constant. We see that velocity goes to a steady state value, and while the efficiency is also increasing, because we saw that starting from zero velocity at the null point, at the stall torque point, the efficiency was zero, and then it was increasing. The current at the beginning, it's very high because of the stall torque, and then it drops down as the speed increases, because we know the back EMF is increasing. So because of the back EMF effect, the available drop in voltage on the resistor is smaller, so the current is smaller, and the position after initial acceleration to reach the steady state velocity, it will evolve in a linear fashion at constant velocity because of the constant velocity. Then if you look at sinusoidal input, we have sinusoidal input voltage, and the velocity will quickly go to this steady situation. I need to check why this is happening so fast. Efficiency is mostly constant because, I know why. So in this case, we start already with the motor in motion. So the velocity was already at a steady state and start to oscillate under the steady state value. But I might change this test and make the robot start with a sinusoidal voltage from still. And in this case, you will see that the velocity will increase as before, but in a sinusoidal fashion, going to sinusoidal motion as well. And this is the way the current evolves, and the position it's increasing in a sinusoidal way as well, but also linearly because you have a steady state average. Sorry, we have an average velocity that integrated creates a trend, a linear trend. Okay, everything clear. Now we can start to get into the hot topic of control. Finally, we have all our ingredients. We have sensors. We know how to select them or to choose which sensors are available. We have our actuator. We know how to choose them. And we are able so to have feedback and to create a control action. We know what we need to adapt the control signal to the actuator signal, which is a motor driver, for example. And now we are getting into the topic where we describe how to design this controller that decides which control action is necessary to achieve a certain task. For example, making our robot, our link, tracking a reference. And if we look to a generic model of a plant, we will repeat here some terms, but now we will provide a proper formal definition of them. You have the plant is the process that you want to control, where you want to act with your actuator, and from which you want the desired evolution. As we saw, we see the process can be represented by a mathematical model. Thanks to that, we can also design the controller based on the mathematical model. Then the output of the plant is our control variable, ym, and these are the variables that should follow the desired behavior. For example, track a position reference. So in this case, if you want to control the position, the control variable will be the position of the angular position of the link. And the UDT U is the control variable. So are the inputs to the plant that affect in some way the control variable and can be manipulated by the controller. This will be, we see the output of the controller. If there is no effect, if the control variable is not able to affect the controlled variable, then it means we have no controllability and we cannot design a controller. Finally, D are what are considered disturbance to the system. So our other inputs, we saw that there can be more inputs to our system that have different effects. One of the inputs of our system is the control variable U coming from the controller. And the other one could be an exogenous disturbance variable that is non-controllable and affects, but by the way, anyway, also this one affects the evolution of the plant and of the control variable, making it making us problem to make this follow, for example, a reference, because this disturbance usually moves away our control variable. And these disturbance, as I said, could be an external torque, cog-in torque, and all kind of external stuff. The controller instead, so the word control refers to analysis and synthesis or design of a control law, and the control law is implemented by the controller, that is the actor of the control system, and in essence, the controller receives an input reference, for example, for the y variable that we want to track, and the y variable that we measure from the plant, and provides as output our control variable u. So thanks to the action of the controller, we will make such, our aim is that our y-m variable tracks our reference. Now, what is the easiest controller you can imagine? We can, for example, define a control law that doesn't take into account ym. We just have the reference. We know we have, let's say, a model of the system that describes the pollution of the system. And using this model, we can kind of invert this model and create a control action that makes such that the ym variable of the plant will follow our reference, will behave as our reference dictates. And a control technique that disregards ym, sensing feedback from ym, is called open loop control. And so it means finding the time history of actuator commands to realize a certain motion. You see, there is no feedback here. And we use the model of the plant to generate UDT. But the performances of the open loop controller are usually poor. You have idea of why this?
Maybe it could be because our model is an approximation of the reality, so we don't take into account everything, and we could have an error that accumulates over time.
Good, this is one point. Another point? Any other? There's no idea. Some ideas.
It can't affect the stability of the system.
What? Sorry. What can affect? Who is this?
The stability of the system. It doesn't change the roots of the characteristic equation.
No, the controller can't affect the stability of the system. Yeah. Okay. Yeah. Okay, let's say the system is stable. It's a stable system, so we don't have to stabilize. Good point. Good point. Yes. What else? You remember about the D variable we were talking? If you have disturbances, they also affect the evolution of ym, and so they drive away from the, if everything is ideal, let's say our model is perfect, as Davide said, and if the system is stable, we could be able to have a behavior of ym equal to r in this situation. But if you have any little disturbance, then this will drift away. If you have modeling accuracy, that doesn't reflect the correct plant, the behavior of the plant, then also we have drifting away. So open loop control, no good. I mean, not good for us at least. Also, sensors and actuators have non-idealities, they are noisy, so these are other sources of disturbance, internal ones. And all these elements create tracking errors, so make YM drifting away from R. So if you have, for example, this is a sample of an electric heater that should regulate the temperature in the room. And to regulate the temperature in the room, you can apply a voltage to the heater such that a current flows inside the resistance. And the current flow generates thermal Joule losses that are transformed into heat. And the Joule losses are related to R to the squared of I. And to regulate the temperature of T of the room inside the room to reach a desired value tau TD, we should apply, we try to apply an open loop control law. We also have a drain of heat because our room is not perfectly insulated from the inside the room to outside. And this is described by the thermic resistance R. Sorry, not by the thermal conductivity. Yeah, thermal resistance across the room walls. For example, there is a window open or stuff like that. And the evolution of the system is regulated by this very simple differential equation. This is also first order, comes from thermodynamics. You have capacity, thermal capacity of the room times the derivative, time derivative of the temperature. So the evolution of my temperature times the capacity is equal to the flow in that comes from the resistance minus the flow out. And the flow out, it's or plus the flow in from the outside. So you can compute the flow across the wall, having the drop in temperature divided by the thermal resistance. And this is the expression. And what we can do here for this differential equation, we know that we want to have a steady state, the desired temperature and at equilibrium. So we consider the equilibrium, setting the derivative to 0. We get this expression equal to 0. And we can compute, given the value of the desired temperature and of the external temperature, we can compute the parameters, we can compute the value of the voltage to apply to the resistance such that the system evolves naturally to the desired temperature after a transient. And this transient, of course, depends on initial condition, that is the initial temperature of the room. But what happens if we change, for example, as I said, we have disturbances, either external disturbances or parametric disturbances. For example, the fact that RE changes, it means that we open the window and there is more thermal conductivity and more heat will go out from the room, reducing changing the dynamic of the temperature. So whatever you computed with this will no longer hold. And also the external temperature can change because low variation. Think about winter or summer, they have different external average temperature. And we see that changing in the thermal conductivity will create a steady state error, and a change in external temperature will also change completely the response additionally, or even a starting point will be different. So we have tracking errors, and this, think about if you have, as I said, a stable system, because a thermal system is something that does not diverge by itself. It's a stable system. But as I said, open loop control is even worse for robotics because we are working with unstable system. There's a mass, you apply a force and this mass diverges parabolically. I create a position that evolves parabolically. So you have if you have a constant velocity force, you create a constant acceleration, integrate, create a linear increase in velocity that becomes, if you integrate again, a parabola. So unstable systems, for a stable system, you need like always a feedback. That's why we come to the idea of feedback of control, closed loop control. That is the controller that exploits the feedback. So the possibility to modify the behavior of the system acting on its input by means of a controller, and being aware of the control variable ym, basing its control action on this knowledge. And the target of a feedback control system is to try to reduce the tracking error, so the difference between the reference and the control variable, and apply the control action according to that. So here you have the feedback coming from the plant output. You have the disturbance still there. It could be either at the input or the output. And in general, on the feedback, we have a sensor. And the tracking error is reference minus measured output or the control variable. And the simplest feedback controller is the bang-bang controller. What is a bang-bang controller? For example, considering the previous example of the room, of a temperature in the room, the simplest controller is the one that switch on or off the heater, reading a thermostat, a sensor, a temperature sensor. And if you have a sensor that measures the temperature, a very simple strategy is that you switch off if the temperature becomes higher than the desired, and you switch it on maximum voltage whenever the temperature is below the desired value, which is what we have in our room actually. However, this in our houses. However, this behavior might generate high frequency vibration that are very bad, very annoying. And an improvement of this controller is to add an hysteresis. Remember the issue that we had in the measurements. One of the possible issues was hysteresis. In this case, we exploit that concept for our good, for our as a solution for the oscillations. So if you put in the control action, if you have an hysteresis, this is usually a relay, which is switching off the heater whenever the temperature is bigger than the desired plus some epsilon, or switching on whenever the temperature is below the desired minus some epsilon. So we have a window for which there is no chattering. Otherwise, the system starts to be chattering all the time because it will always cross around the temperature. And this is bad for the actuator. If you think something like a voltage that goes from 0 to max all the time is not healthy. And so, but still, so despite variations on the external temperature, for example, we increase the external temperature of even 8 degrees, we see that the room temperature is always to stay close to with some vibration still, it depends on the hysteresis size, stay close to the desired value. But of course, this is not the smartest thing to do because, I mean, having such a stupid controller, we can do better. I mean, and doing better is related to the fact that if we want to push the performance, we want to use a model of the plant to design our controller. And in general, to derive the model of the plant, we write down equations, as we did based on intuition, on our physical intuition, and then identify the parameter of this equation, creating some trajectories and measuring both inputs and outputs. And this procedure is called system identification. It's a whole branch of engineering that does only that. So in general, we can design the controller on the model or not, or we can use a black box approach where nothing is known about the internal behavior of the system, and we look only at the input output. So whenever we consider the differential equation based on our physical intuition, we are using we are assuming some internal knowledge on the internal behavior of the system or how the states evolve. But if, for example, if you use a neural network or approach, you look just at the input output. You don't care how it's done inside. Something in the middle is the gray box approach, where the model system is known but with unknown parameters. And you see that in the black box approach, you just look at the response, because the response, for example, the output or the input. So you provide some input, measure the output, and you try to find correlations and to learn this correlation. Everything is clear? Then we should give here, we can give here for the ones that are not didn't do the previous course in control, some definitions. What is a dynamic model? First is the description of a dynamical system, that is an object that evolves over time under some, for example, external input, but not only. You could take a spring and release it, put in a certain position and release it. So you give a different initial condition from the resting state, and this spring will evolve and will start to oscillate. So not only the evolution is due to the input, but also to the initial state. And examples are robotic arm, a car, population of animals, an electrical circuit. There are many different dynamical systems. And the way the system evolves is the dynamics, and a dynamical model is the set of mathematical equations explaining in compact form how the system evolves over time. These equations are differential equations, and they involve the derivative. Differential is they involve the derivative of a function. In our case, of our state, sorry, not a function. This is one. And the state of a dynamical system is a set of variables that completely summarizes the past history of the system and allows us to predict its future motion, its evolution. You can find more resources in this nice course from Alberto Bemporat from Lucca University. And why model is useful? Because the experiments we do on the system, they provide an answer on what we want to know about the system, but they can be too expensive. Think about launching a space shuttle. You don't want to launch a space shuttle. You want to do, for example, simulations before arriving to launch a rocket. Many simulations that can try to predict whatever can go wrong, too dangerous. Think about a nuclear plant, or even impossible. The system doesn't exist yet, so you cannot do experiment of the system because they still need to design it. So you have a drawing, let's say, a CAD drawing of the system. You didn't build your robot yet. In contrast, a mathematical model allows us to capture the main phenomena that takes place in the system, analyze the system, so how it behaves and relations between the variables, and simulate the system. So make a prediction of the behavior after some inputs. And working on a model is advantageous because at zero cost compared to real experiments. We need to consider that, of course, a model is an approximation of the real system, so a simulation it will be as better possible as the dynamical model that is used in the simulation is closer to the real system. But then we have some conflicting objectives for the models. The models to be descriptive enough to capture the main behavior of the system, of all the relevant things, elasticity in the transmission, frictions, non-idealities, and so on, but also simple enough to analyze the system. If you have a very complex model and you want to compute the transfer function, you might take quite a lot of time to compute, or could have a big number of balls. Also, if you remember the time constant we were analyzing in a DC motor actuator, these are description. Think about if you have 10 time constant and you lose the physical insights sometimes on this, and you might have a hard time to analyze the system. It's very complex, the model. There are several types of dynamical system. They could be continuous time, discrete time, linear, and nonlinear, and all a combination of these. So you can have a linear continuous time, nonlinear discrete time system. You can have all the combination. The order of a system is the maximum order of derivative that appear in the dynamic equation. So in the mechanical equation of our DC actuator is a second order, and the electrical one is a first order. We saw that. And a continuous time system is described by a nth order differential equation. And for example, our mechanical dynamics is second order. And we saw from the state space form that we can always transform this nth order differential equation, like the second order one, for example, into a system of first order differential equation. In the state space form we saw was the mechanical one was mapped into two first order differential equations. And this is called the state space dynamics or implicit form. We see it's like that for nonlinear systems. This is the transition equation, and this is the output equation. So this describes the evolution of the state. And this one describes the fact that as output, we might not consider all the state. For example, in the mechanical case, we said the states are position and velocity. We want to just have position. So in this case, the G matrix, the G function is just selecting from the state the one that is of our interest. But it could be that we have a Coriolis force that we want to estimate. So you remember from the gyroscopes that we want to multiply angular velocity times linear velocity. So you have a combination, a nonlinear expression of the states that produce your output. So your output depends on what you want. You decide what you want to see, and you write the output equation of what you want to see. While the state dynamics equation, the state transition equation determines how your state is evolving. And this, which state are from your system, depends on the kind of system, on the nature of your system, on the equation of your system. The order of the system is also equivalent to the dimension of the state. So as you saw before, in state space was a third order system because we have 3 states. And in case of discrete time dynamical system, the dynamics is described by difference equations. And difference equations are the ones that are relating the value of a state at time t+1 to the state at variable t. So this is k. Sorry, k+1 to the value of t at time k. And this is the expression. So in case of linear systems, f and g are linear function of x and u, and a linear system can be represented as this way. We saw this matrix A and B. This multiplies the state, and this is multiplied the input. And the output equation as well can be written in a state space, in a matrix form. So whenever you have a matrix in your dynamics, you're able to represent your dynamics with a matrix product, and you have a linear system. And this is the state transition matrix. What I said, it was the input matrix, and C is the output matrix. This one doesn't have a name, it's just a direct mapping between the input and the output, but usually we don't have. The good thing for what we like linear system is that holds the superposition principle. This means that states these states that the net response caused by two or more inputs, say you have two inputs on the system, the total response of the system is a sum of the responses that the system will have if you activate one input at a time. So you first apply the first input, check the response, and sum up, apply the second input, find out the response, and then you sum up. Summing up the two responses is like the response of the system if you activate both inputs at the same time. And this is very, very important and useful. Allows us to do frequency analysis in the system, which means we apply a sinusoid chirp signal, which is a sinusoid with variable frequency from 0 to whatever we want to see, and measuring the output, and for each frequency we have a response. The matrix, if the matrix A, B, C, and D are constant in time, we are talking about a time invariant linear system. Time invariant. So no dependency of the state matrix on time. Of course, the state, you can be dependent on time. And this is the state space equation or time invariant linear system. And in case of time invariant linear systems, with a certain initial condition, we said that exists an analytic solution for the evolution of the system that has this shape. This is the state evolution, the trajectory of state during time of all the state variables. There can be n state variables. And we have one part, this is natural response, that depends on the initial state. Whatever I told you is a spring. If we move it out from the resting equilibrium point and let it go without any input, it will start to oscillate. And this is the natural response. If you are forcing from externally the spring, then you have with the force, then you have the forced response. And you need to think about a balance on altalena. When you're a child and people are pushing the child, their input force, it's increasing the oscillation if it's done in phase or not in phase. So the force response, it's what we associate to the transfer function that tell us, for example, where are the resonance sources of the system and stuff like that. The exponential matrix here, sorry, this exponential term is exponential of a matrix, which is not the exponential of the entry of the matrix, but it's more complex and has this shape because you can do a Taylor expansion of that. And you can compute the exponential of a matrix with the matter function xm. And so thanks to this equation, we know that having the input signal over time, all the trajectory we want to consider, and knowing the inputs, the initial state of the initial value of the states, we can compute all the evolution of the states and of the outputs for all the time that we want to consider, time interval we want to consider. Everything is clear? Then again, only in the case of linear systems, if you apply the Laplace transform, that as I said, for now we just think about Laplace transform as replacing derivatives with s Laplace variable and integrals with 1 over s, and transforming so differential equation into algebraic equation is not the focus of this course. This is a whole course on control systems to tell you what is Laplace transform, and it's not the focus of this course. But for what it matters for us, we can say that once we apply Laplace transform to our differential equation, we can compute input-output transfer function. The transfer function is something that relates our input to our output, to an output, and we can compute the transfer function directly from the state space dynamics as follows. So we said, remember, x dot is becoming as x, and we have the state matrix. We put on the left, we collect the x on the left, and then if we divide by the inverse of this matrix, this term, and we get the transfer function for the state. We said that our output might not be coincident with the state, but to be a combination of that through a C matrix. So we replace this excess into here, and we obtain this expression for the output. And since the transfer function is the ratio between the Laplace transforms of the output and the Laplace transforms UDS of the input signal, this is how do we compute the transfer function starting from the state space equation. And this can be done with this simple MATLAB command SS and TF. So SS compute the state space system, and then from the matrix A, B, C, D is an object, and then you compute the transfer function representation. And the transfer function represents an external representation of the system in contrast with the internal one of the state dynamics. Think about the same as a black box approach. So from output and input, we have information only on that evolution. We don't know what happens inside the system. And what happens inside the systems could be some additional dynamics that is not observable from the input and output. And this internal dynamics is described by the state space equations, but is not described by the transfer function. So pay attention that the transfer function doesn't tell you everything. And what doesn't tell you, you will understand here, because you can rewrite the transfer function as the ratio of polynomials. So if you compute the previous, do the previous computation of Si minus A inverse, you end up with two polynomials. And from the by analyzing the polynomials, we can get many information. In particular, the polynomial that is most important is the denominator, and the roots of it's called characteristic polynomial, and the roots of the denominator are called pole of the linear system, represented by this transfer function GDS. And if you do the inverse of psi minus A, you will see that the denominator, you have a determinant of this term, and this is exactly the denominator you get. The roots, instead, Zi of the numerator are the zeros of the transfer function. And the transfer function can often be written in zero-pole gain form. So you just rewrite the polynomial extracting the roots. You see that you have the roots of the poles, and in the numerator you have the roots, the zeros. We can underline that the poles are also eigenvalues of the matrix A. Because if you remember to compute the eigenvalues, remember from calculus, you need to solve this homogeneous system. lambda I minus A V equal to 0. And to don't have a trivial solution, so there is a more deep reason for that, that there should be a null space. So a trivial solution is the solution that for which V is equal to 0. You need to have the determinant equal to 0. So solving this, you get the eigenvalues, and you see that this is exactly the same as the characteristic polynomial. So the root of this, that are the eigenvalues, are the root, same as the root of the polynomial that represent the denominator, that are the poles. But in case we have a non-observable dynamics, it happens that the order of the system that is equivalent to the number of poles. So in case we don't have an unobservable dynamic, so everything is observable from outside, the order of the system is the number of the poles of the transfer function and is equal to the eigenvalues of the matrix A. While if you have a non-observable dynamic, so something that you cannot see from outside, then there are some zero pole cancellation, they call, and the number of the poles is smaller of the eigenvalue of the system matrix. Because we said that the state space equation also describes the non-observable dynamics, while the transfer function doesn't. So the number of poles are related to the transfer function are smaller or equal than the number of eigenvalues of the matrix A that describe all the dynamics. Okay, everything's clear now. Then we should define what stability and of equilibrium point is. First, what an equilibrium point is, and an equilibrium point is a couple of state and input for which there is no evolution of the state. So the state doesn't evolve anymore. In case of continuous system, this is whenever derivative is equal to 0. For discrete system, whenever the xk plus 1 is equal to fx. Sorry, I think this is x of k. Sorry, not f. I will correct this in the slides. So the state will remain constant in time. The equilibrium state x bar is stable if for each initial condition, for example, close enough to x bar, the trajectory remains close to the equilibrium state. So it doesn't diverge, it doesn't go away for all the time in the future. This is an idea of stability. And the equilibrium point x bar, sorry, is called asymptotically stable if it is stable and if x converges to x bar for an infinite time. So if the state from whatever initial state after an infinite time goes to the equilibrium for theta to converge for infinite time, then the equilibrium point is asymptotically stable. Otherwise, the equilibrium point is unstable. And we can see here 3 situations where we have a stable equilibrium point. You see that for an initial state here, for example, this is a state plane. So this is an initial state you can present as for a second order system as a point in the state plane. And you have, for example, an input here, and you remain close to the equilibrium, but you don't go to the equilibrium. You stay close. You don't diverge. Okay. While here, from this point you go away. From this point you diverge. So you never get to the equilibrium. While the asymptotically stable one, you have that whatever you start, you converge to the equilibrium point. So these are all the possible trajectories they go. And you need to think about stable equilibrium point, for example, like a pendulum that you move on the vertical, and you will, after gravity and with some friction, it will converge to the bottom, to zero angular position, if you consider the angle about the vertical, and the unstable point we consider as equilibrium point is a pendulum pot reverted on top. So whatever little input you give from that point, it will the pendulum will go away, will go far away. And in the case of a stable equilibrium, for example, you can think about the pendulum where there is only gravity, there is no friction. So you start from that one point and you oscillate back and forth forever with oscillations that keeps the same around the stable equilibrium point, and they never go away. So whenever you have no damping in a pendulum, you have this equation. And you see here exactly this is different initial state, and the state converges to equilibrium. Here the states diverging from the equilibrium, and here are bounded, remaining in a neighborhood. Then, in case of linear systems that we like a lot, we love linear systems definitely because of many things, and one of them is that they have only one equilibrium point. And if the system is stable, and the stability is not a peculiar characteristic, an attribute of the equilibrium point, but is an attribute of all the system. And the system is globally stable. So whatever point, initial state you start, you end up in the equilibrium point if the system is stable. And so stability is a property of the system, not of the equilibrium, like in the case of a nonlinear system, and depends on the real part of the eigenvalues of matrix A. So if you have a linear system, you have a state space equation, you get the matrix A, you compute the eigenvalues, you check how are the eigenvalues. They are complex numbers. Yeah, okay, they are complex numbers, first of all, most of the time, or real numbers. But if you are real numbers, they should be negative numbers. And let's say that we have m eigenvalues, and the system is asymptotically stable if all the real part of the eigenvalues, the real part of all the eigenvalues are negative, is marginally stable, whatever we saw of a circle before, is at least one of them is zero. So if they are lower or equal than to zero, and is unstable if there is at least one that has positive real part. And now that we gave this introduction, we can say now that there are two most common linear systems that we in engineering we always use that represent a big class of many phenomena. And we already talked about that. They are the first and the second order linear system. And these systems are interesting for us because they represent the dominant dynamics of many systems. So if we consider for example, the dominant dynamics is the dynamics that is relevant in a system. So in case of the room example we gave of the heat exchange, we said that the dynamics was first order. Of course, there will be many smaller dynamics that are involved in our room, but let's say the overall behavior in first order. If you think about a tank that is with a hole and the water is flowing out, also that is a first order system. The DC motor, we saw that the electrical dynamic was a first order system. And the first order and the dominant dynamics are is described by the poles that during the transient have the most importance with respect to the other ones. So you can neglect the higher order pole that are not part of the dominant dynamics, and you can use the dominant dynamics poles and still have a behavior that is mostly approximate the dynamics of your system. So with the first order system, we can approximate, we have this dynamics, we have a time constant, we saw that already, and we see that we have one pole, we say that the pole are the root of the denominator, so if you put the denominator to 0, you get a pole in -1/tau, and this is a stable or unstable system, in your opinion?
Always positive. The number is negative.
Sorry? Yeah, I couldn't hear.
It's stable because tau it's a positive number, and so s it's always negative.
Okay.
The real part is negative.
Yeah. Yeah, correct. So this is a stable linear system with a real, in this case, root. Okay, it's a real number because tau is usually a scalar. And the gain of this system between input and output is it's A. We saw quickly saw from the final value theorem that you should put S to 0 to see what is the behavior of the transfer function after when time is infinite. So if you put S to 0, you have A, so Y is AU in case of transient is finished. And while for a second order system, you have this transfer function that you can write this way. You have yeah, you have the term omega n that we call the natural dynamics, natural frequency, and the z term. Sorry, I use this symbol, but it's just because I like more than I'm actually not able to write in Greek the Greek letter Z, but it's not. This is another one. But this is when you saw this, I talk about the damping ratio. And if you compute the roots of this polynomial, you get you get what? You get two solutions, and these solutions are minus z omega n plus minus an imaginary term, because if you compute the roots of this, you get two complex numbers. So you have the real part and you have the imaginary part. And you can see here that the real part is negative. So this is again stable system, second order. And yeah, in general, the imaginary part, it tells you about oscillations. We will see this afterwards. And this is the case whenever z is lower than 1. But if z is bigger than 1, you have two real roots, because if you do the computation, you have whatever under the square root that is a positive number, and so you don't have to do the trick of using the exponential, the complex number I to solve. I think you saw this in calculus. So one root will be minus z omega n plus omega n the square minus 1. And the other one will be minus z omega n minus omega n. And as I said, we have many systems that can be modeled with a first order system. One is the charge of a capacitor, the level of a tank that is flowing out with some constant rate from a valve. Second order system, we have spring mass damper systems. We have RLC circuit with an inductance, capacitor, and resistance. And these two systems have this characteristic response. We see here that this first order system, they can have different responses but have a similar shape. And the second order system, they have another shape. With respect to the first order, there is like a zero derivative at the beginning. So there is like this belly here. And also at some point we get some oscillations. So these are different plots, responses for different level of, for example, of the damping ratio. And how are related poles and transient response? So we said that poles are describing the dynamics, and since the dynamics has to do with the transient, the poles has to do with the transient. And specifically, if we look at the complex plane, so we said we have this complex number, and we have the real axis, that is the real part, and imaginary axis. Imaginary part component, let's say we have here whatever we saw, minus 1 over tau, so a negative real pole. And if we have a bigger tau, so let's think S minus 1 over tau, this pole. If we have a bigger tau, the pole will be at lower or a higher frequency. Any idea? So in general, 1 over tau, big tau, it means 1 over tau small. So the pole will be low frequency. And this means be closer to the imaginary axis, because this is the zero. Here we said it is unstable. Hic sunt leones. You cannot go here. This is unstable. So let's analyze the dominant dynamics. Let's say our dominant pole is here. Our system is fast or slow. It's close to the zero axis, so I think it's slow. I would say depends how close is that. But if we reduce the time constant, 1 over tau becomes a bigger number, and the pole moves to higher frequency, and we have a faster response. So bigger poles, faster response; smaller poles, smaller value of the poles, lower response, lower frequency. And in the case of the second order, it's a bit more complex. You have, we said, 2 poles, and these poles can be complex or real number. So let's say the case where there are 2 distinct real numbers. And so you have a response like this, corresponding to these 2 real numbers. One is at low frequency, one is a higher frequency. Then if you change these omega n and epsilon values, you could have these 2 poles coincident. So a solution in which the square root of that term is 0, and they are both real, and this is called critically damped. The previous one was over damped response. This is a critically damped response. You don't have the belly anymore here. It's like a first order system, almost like. And then if you have another set of omega n of epsilon, you can have these complex roots, especially if epsilon is lower than 1. Sorry, no epsilon, z. If z is lower than 1, you have like this. If z is equal to 1, you have like this. If z is bigger than 1, you have like this. And whenever z is lower than 1, you have complex poles and you have an oscillatory response. That is also called underdamped. Everything's clear? Okay. And if we call the Laplace transforms to map our differential equation into Laplace, we have this one as the first order, and we can compute back the the differential equation from the transfer function, doing this trick. So we rewrite on a single line output and input, and we replace the s with the derivative of the related variable. And this is the differential equation for the first order system that we saw already. It's slightly in a different shape. And in case of a second order system, if we do the same, we get this, and we get the second order system equation in the time domain. So with respect to before, whatever we did was just to put the omega n squared in the denominator and remove from the computing the denominator explicitly. And so we don't have, we have s squared with a different shape for the other terms. Sorry, here is missing s in a second order polynomial. And again, here we have the natural frequency and the damping ratio, Z. And in case of first order system, the settling time we define, we will see afterward what we say is the time that the system needs to evolve to the 5% of the reference signal of the input. The settling time is the time that the system takes to evolve and to get into 5% of the equilibrium value. And in the case of first order system is 4 over tau, where tau is the dominant time constant, the constant time constant of the dominant pole, while in case of a second order system is 4 divided by z omega n. And we have the overshoot, which is the oscillations that the system might have beyond the equilibrium point, and they are related. Of course, we said that oscillations are only happening for second order systems, so we have an overshoot only for second order system. We define this way in percent, and the peak time is the point wherever you have the overshoot in time related to the overshoot point, and the raising time is the time that takes the system to get to the 90% of the reference of the equilibrium point, from 10 to the 90% of the equilibrium point. These are just relations, and if we review how a spring damper is modeled this way, and we said that this is a typical second order system. Let's see how it's possible to express as a second order system and find out what are the natural frequency and the epsilon, the Z and the damping ratio and the responses for this system. So we know that we can solve this differential equation, setting the for the transient we set the input to 0, and we check at the equilibrium. We set the input to 0, and we give an initial input different than 0 for position and velocity. In this case, velocity starts from 0, but it might not be 0. And we study the natural dynamics. The natural dynamics could be expressed with exponentials, and where the roots that we computed before, S1 and S2, are the roots of the characteristic equation of the transfer function, because if you put do the Laplace transform of this goes to the denominator, so it's your input is F, your output is X, and if you put in the denominator, you have 1 over ms squared plus bs plus k. The roots are of this polynomial characteristic are this, and we see here that these roots depends on the value of this argument under the square root. In particular, the system is always stable because we have a negative real part, and this part either will be imaginary or real. But in case it's real, is never making this the real part positive. So a spring down system is always stable, and in case of the argument under the square root is negative, which means d smaller than 2 square root of mk, we get the complex roots, so a conjugate pair of complex number, and we get this evolution, that is oscillation. So we start from the initial state. We said we move the spring out and let it go. We have no inputs, and it will evolve with oscillations. In the critically damped case, we have this at the argument of the square root, which is 0, so 2 real coincident poles, and we have this transient, this behavior in the natural response, and the initial value depends also on the velocity. So if you have a positive and non-zero velocity, you could have something like that. In the third case, in which the argument of the square root is positive, which is whenever d is bigger than this value, we have 2 real distinct poles, and we have this response. And if we increase, let's say this is D actually. If you increase D, you get these shapes. In case of an input that is external, an initial state, we have the forced response, and we have an equilibrium point because the system is stable, so the system evolves toward an equilibrium. And we have 3 cases very similar as before, but going to the equilibrium point. So in the underdamped case, we have 2 conjugate poles, complex poles. In the critically damped case, we have 2 real coincident poles. And in the overdamped case, we have 2 distinct real poles, and we have this value shown up here. And you see that you have overshoot only in the underdamped case. So if we again work out from the previous equation, we try to put in the same form we defined for the second order dynamical system. We find that d we divide by m, these 2 terms, and we find that omega n squared is equal to k over m squared, square root of k over m. And this is the natural frequency, while the damping ratio, it's we can compute it from d over m. We know that d over m is equal to 2z omega n. Then we replace omega n inside here, and we can work out z as d over 2 square root of km. And this is the damping ratio, and we call this critical damping. So you remember, when you have a critical dampers poles of 2 coincident real poles, whenever z is equal to 1. So whenever the damping of our system is equal to 2 square root of Km. Okay, in the case of underdamped, the oscillation are that is for epsilon for z lower than 1. The oscillation are slightly lower than the natural frequency. So the damping, what it creates, reduce the frequency of the oscillations. And you need to think that if you increase damping, these oscillations are reducing more and more till the oscillations disappear and the system has a critical damp or an overdamp behavior. And the system oscillates, the spring mass system oscillates, bouncing energy back and forth between the kinetic energy of the mass and the spring elastic energy, potential energy of the elastic spring. And these oscillations will go forever unless you don't have a dissipative element, a damper. And in that case, the oscillations, they dump out and blow out after a while. So I think we can stop here because we are going over time, and we continue next time with the controller definition and PID, which are the main industrial controllers mostly used in industrial applications, and also in we will give some example on how to design a PID controller and how to tune the parameter of a PID controller. If you have any questions in this part, you can ask.
Professor, excuse me.
Yes.
It's not about the lessons, but there is a bit of noisy in background sound. So I would ask if you could check maybe the video recorder and maybe use a different microphone for the next times, because
oh, you should have told me at the beginning.
No, I can hear you, but it's annoying a bit after a few hours. So if it's possible, otherwise not a big problem.
No, but it was at the beginning or after a while. Now you have it. I changed the microphone. Now you see it. You hear the noise.
Yes, I heard a bit of noise in background. I don't know.
Okay.
Only if you are talking.
Only when.
So yeah. I don't know. Maybe it's only my problem, but
does anybody?
No, it is a general problem. I also hear the noise, but I guess it's just a matter of either setting correctly your microphone settings or
yeah. Okay. Thank you very much.
Maybe you have a lot of amplification in your microphone. Okay.
Yeah. Now you hear is better.
No, but we can test it.
Okay.
ourselves.
Okay. Thank you very much. Okay. Okay.
Thank you.
I have a question. The next lecture will be tomorrow or next week?
Tomorrow.
Okay, thanks. Because there are the degrees, so I don't know if there was the lecture or not. Thanks.
Okay.
But I think that no one is involved.
I will double check quickly, just to be sure. I have a calendar here.
According to the online timetable, there is lecture. As far as I can see.
Yeah. No, wait. No, you're right. No, this week we skip. Yeah, sorry for that. There is no lecture tomorrow. We need to announce this, Octavio. Yeah, tomorrow there are the degrees, and yeah, we skip that. I just checked. Okay, thank you very much. There are other questions? Otherwise, we finish the control part next week, next Tuesday, and we will do the lab control on, sorry, the next Monday we finish the control part, and we will do the lab control on Tuesday. See you, have a good night.